algorithms.
Nice.
Thank you. And today I want to talk about an area of research that is very closely related to things that I work on right now. This is actually a paper that was published a couple of years ago by one of my current collaborators and many of her other collaborators. I know some of you have places to be at around 3:30. I'm going to try to get done by then, but if you need to leave, please feel free. Other thing, if you have any questions about specific things, feel free to ask. And don't worry if any questions seem obvious or not. I'm always happy to hear comments, suggestions, anything of that kind. Okay, so the talk today is going to be about popular matchings. And matching theory, which is essentially the study of assigning people to objects or people to people or just things to other things, has a really long history of more than half a century. And apart from just being very, very useful in everyday situations, there's a lot of algorithms and ideas that are quite powerful, but are also really, really easy to state. And my hope is that in today's talk, I'll get to share some of these ideas with all of you, and you will also gain some kind of appreciation or interest in these algorithms. Okay, so scenario. You are a student looking for accommodation. We have all been in this place. In fact, there are usually many of you who are all looking for accommodation. In fact, again, there may be many kinds of accommodation that we are looking for. So we've got many people who are looking for either places to live. A concrete example of this would be students on campus. And we want to come up with some way of allocating students to houses. This is generally the structure of the problem. I know I said students and houses, but more generally, we can think about this as being agents who need to be matched to objects. This is a bipartite graph. Essentially, it's a graph where we have edges between agents and objects, but there are no edges between the sets of agents and objects themselves. And this sort of captures all the information that we have going into this scenario. Specifically, I'm going to move away from the bipartite graph picture. That's the picture you should keep in your mind. But in some ways, it'll be easier to work with this. Without the picture, it'll make it easier to see the actual matchings we're working with. So we have agents 1, 2, 3, 4, and objects A, B, C, D. And every agent has a set of objects that they consider to be acceptable. They would be okay getting matched to them. The agents have strictly ordered preferences. For example, A has its first choice, 1 has its first choice in A, and then it would be okay with B, but it would be a little less happy. And similarly, it would be okay with D, but it would be the least happy in this situation. This is like one of many possible settings. In the case when we're thinking about students and houses, it makes sense that the students will have preferences over the houses, but not necessarily that the houses have any preferences. They are just looking to have a tenant occupy them. They don't really mind which tenant it is. You may have other situations where you want to match people to people or people to jobs, in which case the jobs definitely have some kind of a preference over which candidates they would like to hire. And in fact, jobs may actually look to hire multiple people. So we're actually not going to be talking about a lot of those settings in this talk, but something worth keeping in mind, because that will also inform the kind of results we're able to get. So here's a couple of examples of matchings. I have not stated explicitly, but in this situation, we're sort of considering a one-to-one linking between every agent and one of the objects. So over here in red, we have one matching, and in purple, we have another possible matching. The question is, which matching is better? This does not have a mathematical definition as of everything I've said as of yet. It is sort of up to us to come up with some notion that we count as better or worse. In fact, this is generally motivated by what you are trying to accomplish in your matching problem. Some examples would be allocation of campus housing, and there was actually some empirical study done, I believe, with colleges like Stanford, where they tried to find a way to allocate students to their dorms. But you may also have a situation where you're assigning teachers to schools, doctors and nurses to hospitals, and your setting may affect the type of matching you're willing to accept. So this is the point where I would ask you to sort of just think about what you think would be a reasonable matching. If you were a person who was handed a house, how how happy would you feel with your match? And what would make you really mad? Or you go back and you send an angry email saying, actually, this is unacceptable, I would like something else. But the notion that we are going to work with is popularity. And this is actually very interestingly, I didn't know this until very recently, presented by Peter Gardenfors in a behavioral sciences journal. His inspiration was actually the classical stable matching problem, in which case you have both sides of the graph have preferences over each other, and we have this notion of a stable matching. Gardenfors was actually trying to sort of think beyond that and think of what other notions we could come up with. And the notion he described was actually popularity. So these were the same two matchings that I had earlier. We had the purple one and the red one. And essentially what we do is we ask every agent to vote for the matching that they prefer. So head-to-head vote. In this case, 1, 3, and 4 all prefer the purple matching because remember, all the preferences are strict. So they are very clearly like, yes, we prefer the purple matching. Whereas agent 2, I think I might have flipped the colors here. Well, in that case, it's different, did I not? Okay, cool. And there is only one agent who actually prefers the red matching. So in this situation, we sort of have a clear winner. We would say the matching BCAD defeats DBCA. And this is going to be the notion we use to sort of say that a matching is more popular if it gets more votes. So more formally, our instance is a bipartite graph where agents in set A have one-sided preferences. And we say that a matching is popular if there is no other matching M prime, such that the number of agents who prefer M prime exceeds the number of agents who prefer M. Some of you who have maybe seen some game theory-esque ideas may have heard of this concept of a weak Condorcet winner. That is a matching or a team that is not defeated by any other. However, as in the case of a weak Condorcet winner, one of the potential drawbacks of using this notion of popularity, which seems quite natural actually, saying that we have a matching that is completely undefeated by anyone else, seems like a good notion of a matching that we would want to assign, because everyone seems to largely agree that they prefer this matching to every other one. However, there are instances where there may not be a most popular matching. This is one such instance. Take any matching, in this case 1A, 2B, 3C. Note that we can improve the matches of agents 2 and 3 by moving them 1 up in their preference list, and then we will knock agent 1's match down to C. We have improved our matching because 2 agents are happier and 1 agent is sadder. However, now that we've improved our matching, we know that we can do this exact same procedure again. Improve the matches of 1 and 3, improve, give 2 a worse match. And we can do this for a 3rd time, basically to end up back in our original matching. So the notion of a popular matching, or even a weak Condorcet winner, some of you might have seen this in like voting systems and stuff. Technically, such a matching does not exist in all instances. So there's a couple of points here. One is noting this fact. Is there a good way that we can figure out if such a matching exists? And if there is such a matching, how hard is it to actually find one? And I will say, keep these sort of chains of improvement in mind when we think about the idea of comparing matchings to each other. What's the total number of matchings that are possible in an instance of n agents? It's n factorial, right? So technically, you would have to take n factorial, choose too many combinations, and have everyone vote. That is completely intractable. However, this notion of these chains of improvement actually will give us a very, very nice, clean characterization of when a popular matching exists and how we can find it. Okay, so to start off with a bit of terminology. So in our instance, we have agents and they have lists. You will notice that every agent doesn't have to like every object. We will add a dummy object called a last resort object that is denoted L of 1 for agent 1. And this is basically the last resort that they can get matched to. It is less preferred than every other object. This will essentially allow us to look for a perfect matching in our new instance. That is a matching that matches every single agent. However, if an agent does end up getting matched to their last resort, they will end up unmatched in the final matching. This is more a sort of supplication that will allow us to solve the problem a little more easily. Any questions about anything I've said so far? All right. So a good place to start seems to be everyone would love to get their first choice. So let's try to do that. Let's try to give every agent their first choice. For every agent, they point to the first object on their list, highlighted in red, and this is their first choice. An object that is the first choice of some agent is called the first choice object. And every agent will sort of mark this off on their list. We would like to match as many of these objects as possible, because when you get matched to your first choice, you're not really looking to improve anything and you're pretty happy. However, in this case, we notice that there are ties. Both agents 1 and 3 have the same first choice. So we need to come up with some way to resolve this. So we have the notion of second choice objects. Every agent highlights their first choice object. Then all first choice objects get taken off the table. So now A is unavailable and C is also unavailable. Agents now look at the remaining objects in their list and pick the highest one available. So we notice that agent 3 does not have C as its second choice object, even though it is the second most preferred. That's because C has already been sort of claimed as a first choice for agent 2. Important point, this is sort of very important for the characterization, is the set of first and second objects are disjoint. It should be pretty clear why that is from the definition. But yes, they are a disjoint set of objects. And very amazingly, this is truly incredible to me when I saw this for the first time. We say that a matching is popular if every first choice object, that is one of the red objects, is matched to an agent who has them as their first choice, and every agent gets either their first or their second choice. We have gone from the whole universe of possible matchings, and we are restricting ourselves to only the matchings where every agent gets either their first or their second choice. So the agents who get their first choice, they're chilling, they're very happy. But the agents who get their second choice, it somehow seems like, maybe it's not so bad. They didn't get their first choice, but the actual match they got was maybe not so bad. And this is the entire characterization. When I first came across the definition of popular matchings, I felt it was a little unwieldy because we're thinking about head-to-head elections, but this is sort of the entire characterization that we. So the algorithm then becomes this. We draw a bipartite graph of all of the agents with edges for all of the agent's acceptable objects, and we basically delete any edges that did not satisfy this criteria. And then we look for a perfect matching. There are many nice polynomial time algorithms that will find you a maximum matching in a graph. And if you can find a perfect matching, that is your popular matching. If you cannot find a perfect matching, there is no popular matching in your instance. If you can't find perfect matching, you just didn't have enough objects to go around, therefore there is no popular matching.
Excuse me, but the
Yes.
perfect matching may not satisfy your first bullet item, right? So you have to be a little careful. So you said just for every person, just connect them to their first and second choice and see if
So
there is
you
no-
take every person and the only edges you allow are to their first choice and their second choice. Their second choice might be a last resort item. And every agent has a unique last resort item. So they can always be matched to that. However, consider the instance ABC, ABC, ABC. All the first choice objects are A, and all the second choice objects are B. So we have 3 agents and 2 objects.
Yeah.
So you cannot find perfect matching as in like the max matching doesn't match all of the agents.
Yeah, no, what I meant is I think you said algorithmically just take the pruned graph where every
Yes.
person is only connected to their first and second choice and see if this graph is a perfect matching.
Yes.
So there is a popular matching if and only if there's a perfect matching. But
Yes.
but an arbitrary perfect matching may not satisfy your first bullet item, right? It may
Right.
miss the first preferred first choice objects. Is that not true?
Yeah, so I guess, yeah, so yeah, I should be a little careful there. You do have to make sure that the first choice objects get matched to the first choice neighbors. As long as they are all matched, this will work out. Okay, that is a good point. Okay, let us briefly see why this is enough. Why is it enough to only look at two levels, the first and the second choice? In essence, if we only match agents to their first and second choices, we are avoiding that chain of improvement we had earlier, where we can bump two agents a choice up by one each, and then demote one agent by one level. So suppose we had an agent one who is mapped to an object, who is currently matched to an object that is not their first or second choice. This agent has a second choice object that they prefer, and that is matched to some agent two. Suppose there was no agent two, we can already improve the matching by just assigning one to the green object. So assume that there is an agent two. Now agent two is matched to this second choice object. They must have a first choice object as well. This is because the set of first and second choice objects are disjoint. So two actually does have one more level it can look up to. It is currently matched to its second choice, but it could be matched to its first choice. And because all first choice objects are matched, the yellow object must be matched to some agent three. And this is exactly that chain we were looking for, where we can sort of promote agents one and two, and we demote agent three. We just unmatch agent three, maybe it gets another object, maybe it doesn't, that is unimportant. We have found a more popular matching. And this is sort of that idea of this characterization sort of captures everything we want to say about popularity. I won't go into the proof for the other direction, but if you ever want to read it, the original paper, Popular Matchings, by Abraham et al. Is a very nice paper, actually. Okay, remember how I said the original situation was students in housing? Would it not be very awkward if you signed up to get matched, and then they said, sorry, you got your last resort, we don't have a house for you? That seems like it would be a pretty bad situation to be in. It turns out there are cases when, even more than popularity, we care about the size of our matching. And I believe one of the authors on this paper, Kavitha Telikepalli, was saying one of the motivations was the COVID pandemic. When you want to assign nurses to hospitals, it is more important that every hospital gets a nurse than the popularity of the matching. So we are now interested in what is the popular assignment problem. This instance does not have a popular matching. We can check that in the same way we did before. However, we are only interested in perfect matchings. So what if we only consider the set of all perfect matchings, and we say, let's take the most popular among the perfect matchings? And an assignment is basically a perfect matching in this case, as in we want every agent to receive an object. And a popular assignment is basically the most popular among all the assignments. We'll see here that even though A, B, and C are matched, even though this is not a popular matching, if we try to do that chain of improvement, even if we promote agents 2 and 3, we still require the matching to be perfect. Therefore, there is no one agent 1 can be demoted to. So in some sense, we've sort of relaxed our earlier idea to have this connection. Okay, now we're going to shift a little from talking about a combinatorial characteristic.
Sorry, I don't understand what a most popular perfect matching is. So popularity is in comparison between two matches.
Yes.
So take the
So
family of all perfect matches. So how do you define most popular?
it's the same thing. You put them to head-to-head vote. All
again,
perfect matchings with each other, they get put to a head-to-head vote.
there may be no winner.
There may be no winner. The same counterexample I gave in the very beginning also holds for this. So there may not be a popular matching. So you may have no popular matching, but a popular assignment, but you may also not have any popular assignment.
Oh, sorry, what's a popular assignment?
So a popular assignment is the most popular assignment among perfect matchings. It's the most popular perfect matching among all perfect matchings.
Yeah, that's what I don't understand. So what do you mean by most popular?
Same idea, you just take the bag of perfect matchings, you throw everything else out,
Okay,
and you put those to a head-to-head vote.
okay, so whoever beats the most other,
Yes, whoever is
Perfect.
undefeated, yes.
but that's not guaranteed, right? So that's
It's
what I.
not guaranteed.
So what do you mean by most popular assignment?
Yes, so in this
I
case,
understand, yeah.
so there is no popular matching here, right? However, let's look at all the assignments in this instance. We only have ABC and BAC. You can compare those two against each other, and actually in this case, it turns out they are both equally popular. But that is the assignment you're looking for. So basically, you're looking for a perfect matching, and in the previous case, we were allowed to improve a matching by demoting someone and just kicking them out. Here, you're not allowed to do that. If you have to demote someone, you have to then find them another match. You have to go and then sort of reshuffle the whole. It is an interesting idea, though. It took me a little while to wrap my head around. But I guess for now, sort of think about it as we require every agent to be matched. There are no last resort items anymore. But no, thank you. That's a very good clarification to have. And we're also going to switch tacks from this more combinatorial characterization that we had, where we had this first choice, second choice. We're actually going to switch to the world of linear programming, which is always very reliable, really is old faithful in a lot of these combinatorial optimization problems. So the approach here, and we will see that this both solves the popular assignment problem, but it will also actually give us a lot more flexibility in terms of the setting that we're considering, and we'll see that soon. I know that many of you are familiar with linear programming, and if any of you are feeling a little rusty or maybe have not seen this in a long time, that's totally fine. I will try to give some high-level intuition and give some nice pictures that will explain what's happening. So first, we're going to fix an assignment M. Remember that we're saying an assignment is a perfect matching. Every agent is matched. So sort of think of this as like maybe a default, like pick some assignment that you like. Every other assignment that you want to compare to our earlier matching M, every agent comes up with this cost function. It looks at the match it gets from M, and then it looks at a new incoming match that it gets. And if it prefers a new incoming match, it has a cost of +1. Like it would prefer to jump ship and go to the match. If it prefers its current match, that's a cost of -1. It's sort of like, no, I'm already happy where I'm at. I don't really mind if I move or I don't move. I don't want to move. And the third case is the little tilde is basically indifference. In our strict preferences case, we don't have indifferences, so you can think about if the matches are the same in both cases. And that gives rise to this very nice compact LP. You will recognize this as the LP for finding a perfect matching in a bipartite graph. This constraint over here essentially ensures that every vertex is matched to exactly one other vertex. Not at most, but exactly one. And this cost function is going to be, remember, the cost is positive if the agent wants to jump ship to a better matching. It's negative if they want to stay at the current matching. And it is 0 if it's the same matching. So it turns out the optimal solution to this LP that we'll find as our popular matching is the one that makes all of the costs equal to 0. So the optimal solution is going to be 0, and that is equivalent to our most popular matching. So yeah. Any questions about the LP so far, or any of the definitions I've given? It's been a lot of definitions. Yes, okay. Is popular defined to be the uniquely best in popular matching? Can you read the whole question?
Yeah. So it's popular defined to be the uniquely best in popular matching, while how popular is defined as number of assignments worse than it.
Right,
Popular
so
assignment.
the popular matching does not, or the popular assignment, neither of them needs to be unique. There may be many different matchings that all have like the same number of votes for them. You can imagine like, oh, there's 2 matchings and one prefers the first and 2 prefers the second. So they kind of balance each other out. So it's not necessarily unique. In regard to the second part of the question, I think it's maybe more, you have a notion of allowing some amount of unpopularity. So if you want some kind of an approximate solution that's not popular, but is a little unpopular, there is some notions of that, but we're not really gonna get into that. Yes.
Can you explain the cost function? I don't understand like the dependence on M and how you're using that to define the cost of an edge specifically.
Yes, exactly. So it's a good question in the sense that we don't actually, and it's not a specific matching. The idea is more that it is when the variables are set to equal the most popular, the actual like most popular matching, everything will, or the cost will actually zero out. So when you solve this equation, you basically will end up getting optimal perfect matching. Sorry, the optimal popular matching, not perfect matching. We're not actually using a specific matching M, it's more implicit. But you can write out this explicitly.
But if you don't have M, cost M is undefined, right? So I understand that if somebody gives you a candidate M, you can write this LP and it will certify if M is popular or not, right?
Yes.
That I understand. But if M is not specified, what do you mean by cost M? You can't write this LP, right?
So in the sense that what you have is basically this is we don't explicitly solve this LP. I will say that. So we don't actually explicitly solve this LP. The reason we have this LP is actually so that we can write its dual, and then we will develop a primal dual algorithm. So yeah, maybe I should have started with this up front. So this is maybe more of a theoretical exercise than an LP we're actually going to solve. So in your minds, you can fix the matching and just sort of imagine what would happen if we substituted any other matching in relation to that. Okay. As mentioned, we are going to do the great thing where we take the dual of the LP. I recall that the dual of the LP, in some sense, you can think about the value that a dual solution gets is an upper bound on the primal LP, which is this LP. For our purposes, we know that the objective value is going to end up being the same. However, what we want to do is if we can somehow find an optimal dual solution, that will then give us an optimal solution to our primal, which is exactly what we want. Well, I will say this again, so maybe it's more clear. What that means is we're going to use the fact that if I have a solution that satisfies the dual constraints, these are some numbers YA and YB, where A is for the agents and B is for the objects. If I can come up with some numbers that satisfy this equation, I will have found a popular matching, and these numbers will be my certificate that says that we have found a popular matching. So our entire job, even though we have written these two LPs, is actually to find some way to come up with what these numbers should be. And that is going to be what our primal dual algorithm is going to try and achieve. For those of you who have seen maximum matching LPs before in a bipartite graph, it turns out that both LPs actually, all of their optimal solutions are integral, which means that the optimal solutions for these numbers y and yb, these are integers. So they are 0, 1, 2, 3, all the way up to n, and they are 0, -1, -2, all the way up to -n. Which makes our life very, very simple. This is because of the constraint matrix itself. It's a property called total unimodularity, if anyone's interested. But the reason this is great is because we somehow only have to do some kind of a search function or search operation looking for YA and YB in these finite sets. And if we can find one that satisfies the constraints, we are good to go. In order to actually describe the algorithm, I really briefly will define an edge, not an edge. I will define a graph. What we are going to do is we are going to take all of our objects B, and we're going to assign them numbers or levels. those levels are going to correspond to the YB values that we want to find. And given a potential assignment of these YB values to all of the objects, we are going to define a graph called G prime. Do I have a picture for this? Okay, maybe I will just show this picture and then I will go back to the.
Is the level the current Y value of a vertex?
It will be the current Y value of the object, that is true, but the agents, it will depend on which object they get matched to. So suppose this is the current level assignment where A is at 0, B, C are at 1, and D is at 2. For every agent, they look at their neighbor that is in the max level, and they put an edge to their most preferred neighbor in the max level. They also put an edge to their most preferred neighbor in the level right below it. So every agent has either one edge going out at its max level, or it has two edges going out to its max level and one minus that. So that was the definition I had over here. Here it is in words. And I kind of want you to think about this as the max level edge as being that second choice object, and the max level minus one edge being the first choice object. So this is sort of saying that one of these options is technically better for the agent, but they are able to get matched to either one of them, and they don't know which one they're going to get. What's going to be different here from our earlier characterization is that the first and second choices can be much further down the list in any agent's preferences. Any questions about this G prime definition? Okay, and here is the primal dual algorithm. It is quite simple to state. So what we do is for all the objects, we put them in at level 0. While the levels are strictly less than n, this is because the max allowed level for any feasible dual is n, so that is when we have to stop. We construct this graph and compute a maximum matching. If it's a perfect matching, it turns out it is a popular matching. If it is not a perfect matching, we just take every vertex, object vertex that is unmatched, and just bump its level up by 1. And we rinse and repeat until either we find a perfect matching, which is popular, or some object exceeds its maximum allowed level, and we know that there is no popular matching. I'm going to run through a really simple example because I think seeing this actually kind of work is a little cool. So here we have these preference lists. This instance was mostly chosen so I could draw this nicely. As you can see, every agent has its most preferred object is A, so they're all connected. We then move B, C, D up to level 1 because we weren't able to find a perfect matching. So now we can see that every agent has two edges going, their first and their second choices. C and D are still unmatched. To make themselves more desirable, they move up another level. And this sort of forces agent 3 to move all the way to having an edge to C in level 2. Finally, D is still unmatched. It has no choice. It has to move higher one more level. And at level 3, D gains an edge to 4. We now have a perfect matching, that is ABCD, and this turns out to actually be a popular, not just popular matching, but a popular assignment. This instance does not have a popular matching, per se, but it does have a popular assignment. So we basically run this algorithm until we find a perfect matching, and that is popular. I want to highlight what the dual is doing over here. What are these levels doing? And why did we need D to rise all the way to level 3 in order for it to gain an edge? So these are what the dual values are going to be. The dual values of objects, which is this YA, YB, YC, YD, that's based on the level they were in when we stopped the algorithm. And it's the negation of that, because remember, we want all the values to add up to 0. The agents get their value as the positive version of whatever their matched object's level was. So if 4 got matched to D, its value is going to be positive +3. this is the matching, these are the duals. Let's think about what's happening here. Agent 4 got matched to D, but agent 4 does prefer C to D. Why is something like that? How does the dual capture this relationship? Remember, if we have an actual optimal solution to the dual, we know that it is going to be a popular matching by our primal dual LPs that we had. The constraint we need to satisfy is YA plus YB is greater than the cost of the edge. If N is going to be my actual popular matching ABC, if I considered any other matching where 4 actually got matched to C instead, that cost number over there would be 1 because 4 prefers C to D. So I somehow need to make sure that this difference in values is at least 1. And that is true. We can see that where agent 4 had to get matched to someone in level 3 in order for there to be a difference of 1 between its actual match that it would like and the one that it actually got. So this difference is sort of captured by this G prime graph. If an agent prefers a different object to the most popular matching, the dual actually needs to reflect this difference and shows that it's still actually such a matching would actually not be popular. Our original matching is in fact the most popular. I won't have time to go into the actual details of the proof here, but the proof idea is this. The statement is, if an instance has a popular assignment, then there is a function of levels L assigned to all of the objects that corresponds to a graph G prime that contains a perfect matching. The forward direction for that comes, okay, the direction that says, if there is such a level function, then there is a popular assignment. This follows from duality, and the fact that we can find such an optimal solution for the dual means that we can find an optimal solution for primal, which is our popular assignment. The backwards direction, which is where if M is a popular assignment, we can construct a level function for it. That actually follows from using complementary slackness. Essentially, the idea is, given a popular assignment, you can look at all the edges in your assignment. And because in the primal, those edges will have a positive value in the objective. Hence, in the dual, those inequalities must be tight. So those inequalities must be equal to 0. From that, we can then reconstruct some levels that will satisfy this. Hence, we will be able to find such a level function and such a G prime that shows that the other direction works out as well. Other great features of this algorithm. Earlier I said that this not only solves a popular assignment problem, but one of the reasons it is sort of a great step forward from even previous work is it solves the original popular matching problem with ties. Well, the case of ties was resolved earlier, but it also resolves with the case of partially ordered preferences. So our earlier assumption was that an agent prefers A as its first choice, B as its second choice, C as its third choice. However, what happens if agents' preferences aren't so clear? Sometimes preferences are induced by cardinal preferences, where you have numbers. So for example, let's say I value house A at 10, house B at 12, and house C at 14, where I have this difference of 2. I'm willing to say that, yeah, house A and B are kind of comparable for me, house B and C are kind of comparable for me, but A and C are just too far apart. Those are different. Those are called semi-order preferences, and they would be captured by this graph, where A is preferable to C, but B is kind of indifferent to both of them. This primal dual approach actually handles this case without requiring any extra machinery at all. In addition, we can also find popular matchings with some margin of unpopularity, where there is some levels in between finding a popular matching and finding a popular assignment. the more levels we have to force the objects to go up, we are increasing the unpopularity in some sense. As in, we are forcing agents to get matched to objects that technically they don't really want to, but we are making them do it for the sake of getting a perfect matching. And because we can find maximum matchings in polynomial time, and we only have to try n squared many levels, this whole algorithm runs in polynomial time. One last thing I wanted to say was that this is a lot of technical stuff going on, but at the high level, this is the idea. Agents all try to go for the best objects they can get. And this leaves a lot of undesirable objects hanging around. So what these undesirable objects decide to do is they raise their level to make themselves more attractive. And we require agents, if they have an undesirable object at a higher level, to sort of move along with them. And this sort of almost like stratification in some ways. We sort of have all these objects moving all the way up until there are enough edges that all the agents can get matched to all of the objects. We started off in like a behavioral sciences journal, and we sort of see that there's some high level intuition or maybe some kind of behavioral sciences interplay going on here. Anyways, I think that is all I had to say. Here are the main references for the papers that I talked about. Any questions, comments, or feelings, I would be happy to hear. But yeah, that's all I had.